Assalamualaikum and good day everyone. So in this lecture, I'm going to share how to solve a second order differential equation. So I will first explain about second order linear ODE, discuss about the general solutions, and go through two different uh, types of second order ODE, which are ODE with constant coefficient and Euler-Cauchy equation. Right. Before we proceed, let's have a short recap on a fundamental concept to solve quadratic equation. So the standard form of a quadratic equation is ax squared plus bx plus c equal to 0. And as you all know, there are many methods of solving the quadratic equation. And the easiest way is to use calculator. So please figure out and remember how to find how to solve the quadratic equation using calculator before you proceed with this video. All right. So when you find the roots of quadratic equation, we will stumble upon three types of roots: real and distinct roots, real and equal, and complex roots. So it depends on the determinant term here. Determinant can be calculated from b squared minus 4ac. If it's more than 0, then it has real and distinct root. If equal to 0, it has a real and equal roots. If the value is less than 0, then it has complex roots. So what does the three types of roots means? So I will share a graph here. All right, let's see. So firstly, for this the real and distinct root, this is the example actually. So when we alter the value of a, b, and c of a quadratic equation, basically the graph will move. So for example, for this case, the curve of quadratic equation intersects at y-axis at 2 points, around -4 and around 0. This means that the root of this particular quadratic equation, when you plug in these values into your calculator, you will get two different value of x, or in other words, you will have two different value of roots. And this is what we called as real and distinct roots. Means you have two different roots, -4 and 0. All right. So for the second case, when at this point, you will actually get only one point of intersection here. So this is what we call as real and equal root, where when you plug in this quadratic equation into your calculator, you will only get one value of x. For this case, the x is 0. Now the third case, whereby the quadratic curve does not intersect the x-axis at any point. So this is the case for complex roots. When you solve this quadratic equation, then you will have two different complex roots. All right, I hope that is clear because this is very crucial for the next step. Going back to our lecture slide. All right, if you want to access that interactive plot, you can click to this link here. Now, let's try to answer part A of the quiz by yourself first. If you haven't done the quiz, please pause this video and continue when you're done. Okay, so let's see what's the answer. For the first quadratic equation, the type of fruits is real and distinct. Also for the second one, for third and fourth equation, the roots are real and equal. And for the fifth and sixth equation, the roots are complex roots. So you can determine the types of roots based on the values that you get from the calculator. If you get two value of x, then the roots is real and distinct. If you get only one value of x, then the root is real and equal. When you have complex roots that can be seen through the I term here, then your root is complex roots. Please remember how to determine the types of roots because it's important for the next step. Order ODE, that is linear and homogeneous, there are various types. So we are only covering second ODE with constant coefficient and second ODE for Euler-Cauchy equation. So let's see what is the meaning of second ODE with constant coefficient. So this is a general formula of a um, second ODE with constant coefficient. Coefficient means the value in front of the dependent variables here. So A in front of y double prime, B in front of y prime, and C in front of y. Since A, B, C are constant terms, meaning that there are no x or t terms, then we call it constant coefficient. So for this case, for Euler-Cauchy equation, the coefficient in front of the dependent variables are variable coefficient, means that there are additional terms of variables in front. So for Euler equation specifically, in front of y double prime, there is a term of x squared, and in front of y prime, there is the term x here. So how to solve both equations? So if you see here, this linear homogeneous second ODE looks like quadratic equation, right? So you can see y double prime here looks like y squared, and y prime here looks like y power of 1, and y here looks like 1, can be reduced to 1 actually. So how to solve? We first have to convert the y term of the ODE here, this ODE, into quadratic equation in terms of lambda. Why? Because we already know how to solve quadratic equation. That is why we want to convert this ODE, simplify it into a quadratic equation so we can solve the equation. So after the second step is to solve the quadratic equation and find lambda. After we find lambda, we convert that lambda back to y and find the general solution. So if the boundary condition is given in terms of values, for example, x equal to 1, y equal to 1, then you can use that condition to find a and b. I will explain about a and b later. And when we substitute the value, after we get the values of constant a and b, we will get a particular solution. So the general solution is in this, if you plot the graph, general solution, we will have this kind of graph where the equation is actually a family of solutions of many lines. So if we are given an initial condition or boundary condition of values, then we can get only one linear, one line or one curve of particular solution. All right, let's see how to convert this linear homosecond ODE, both of these, into a quadratic equation. So let's see for constant coefficient first. So we assume that y equal to exponent lambda x. So some genius mathematicians have done the calculation, have done all the steps. So we just use this assumption because this will lead us to converting this ODE into a quadratic equation. So we substitute the y assumption into our ODE. So finally, later we will get this characteristic equation that can be used to convert our ODE into quadratic equation. All right, for Euler-Cauchy equation, the assumption is a little bit different here. So for constant coefficient, the assumption here is y equal to exponent lambda x. For Euler equation, on the other hand, is y equal to x power of lambda. So we substitute this assumption into the ODE, and later we will get this characteristic equation that can be used to convert Euler-Cauchy equation. This is Euler-Cauchy equation into a quadratic equation. All right. So this is the final characteristic equation. And after we get the lambda values, we can convert that to y and substitute into a general solution. This is the general solution for second order ODE. Y equal to a y1 plus b y2, where a and b are constants. So this general solution is based on superposition principle, which states that for linear ODE, if y1 and y2 are solutions to an ODE, then the linear combination of y1 and y2 is also a solution. So it's very complex. So if you want to learn more on the principle, you can go to this YouTube video, but but you can take this equation as it is and continue with the next step. All right. So, but bear in mind that quadratic equations have different type of roots. So remember, if we have distinct roots, we will have two different value of lambda. If we have equal roots, we will have only one value of lambda. If we have complex roots, then we will have complex numbers of lambda. So this will affect our terms of y1 and y2. So let's go through each cases one by one. So for the first case, for distinct roots. Now, the general solution is y equal to ay1 plus by2. So based on previous assumption of y, y1 is equal to exponent lambda 1 x, and y2 is exponent lambda 2 x. Since we have lambda 1 and lambda 2, then we can get two values of y. Now we can substitute this y into the general solution. So we will get y equal to a exponent lambda 1x plus b exponent lambda 2x. So I also provide a derived general solution if you want to use it later. All right, for the next equation, for Euler-Cauchy equation, it has the same general solution because both are linear and homogeneous ODE, second ODE. But the difference here is again the y assumption, where for y1, the assumption is x power of lambda 1. For y2, the assumption is x equal to lambda 2. Again, we substitute the value of y1 and y2 into the general solution, and we get this general solution specific for Euler-Cauchy equation. And I also provide the derived general solution here in case we need it later. Okay, now let's see an example. So solve y double prime plus y minus 6y equal to 0, given that y at 0 equal to 1 and y prime at 0 equal to 7. So the first step is um, to know the characteristic equation to solve lambda. So we know that this is ODE with constant coefficient. So this is the characteristic equation. Remember, we have different characteristic equation for Euler-Cauchy equation. So please remember which one to use. Yes. Next step is substitute A, B, and C and solve for the value of lambda using your calculator. Since there are two different values of lambda, then we know that it is a distinct root. So for distinct root, the value of y1 and y2 are exponent lambda 1x and exponent lambda 2x. Substitute into the general solution, and uh, we get this value of general solution y equal to a exponent negative 3x plus b exponent 2x. So when you plot this, it will come out as multiple curves. This is what we call a family of solution. Now, um, let's continue first with the second ODE with constant coefficient. So when we have the general solution here, and given the initial or boundary condition in terms of values, then we have to find the particular solution that will lead us to the single curve line. So we have several options to do this, to find to, to do this. And for the first option is to do manual derivation to find y prime, but I already provide a derived general solution in the previous slide. Let's see here. So you can memorize this derived general solution and substitute the values of lambda, or you can manually derive it. This option is up to you whether you want to do manual derivation or you can do substitution. Eventually, you will have equal answer for both methods. All right. After you get the y prime general solution, you can substitute the value of the boundary condition here. For this case, x equal to 1 and y equal to x equal to 0 and y equal to 1. So y here equal to 1, x here equal to 0. And you can find the value of a. And for this one, you can substitute the value of y equal to 7, y prime equal to 7, and x equal to 0. And you can get the value of b. After getting the value of constant a and b, you can substitute to general solution and get the value of and get the particular solution. All right. Let's see for Euler equation. Okay. So for Euler equation example, so solve x squared y double prime plus 4xy prime plus 2y equal to 0. So it's very easy to determine if an ODE is second ODE with constant coefficient or Euler-Cauchy equation. So please make sure you know what type of second ODE by looking at the terms in front of y double prime and y prime. So if there is an x square here and x here, it means that you are dealing with Euler-Cauchy equation. So the characteristic equation will be different, and also the y assumption will also be different. So for this case, the characteristic equation is this equation. So the difference here is for constant coefficient, the value in front of lambda is b. For Euler-Cauchy equation, the value here is b minus a. So substitute all the ABC values and solve using a calculator. And then you know that it is distinct roots, and you substitute the values of general solution, and later you will get the general solution. When you plot this, y equal to ax minus 1 plus bx power of negative 2, you will get this graph, a family of solutions. Now, when you get this general equation, since that the initial conditions are given, then you have to do derivation to get y prime. So again, you have two options. You can do manual derivation, or you can substitute to the derived general solution that I have given in the previous slide. Both methods will give you the same answer. Now, after getting the y prime equation and y, you can substitute the value of initial condition given and can calculate the value of a and b. Substitute the values into the general solution, you will get the particular solution here. And when you plot this, you will get this single curve. All right, let's see a simplified answer so you can get the idea better. So when you have a question to solve and a second order ODE, determine which type of ODE that you are dealing with, either it's constant coefficient or Euler-Cauchy equation. So for this case, constant coefficient, you use this characteristic equation to convert the ODE to quadratic equation. Second step is to solve the quadratic equation to find lambda. After finding lambda, you will know which root that you have. So if it's distinct root, the y assumption will be for lambda 1 and lambda 2. Substitute it to the general solution. Then you will get this general solution here. Now, since the initial condition is given, then you have to derive the general solution to get y prime. Substitute the value of initial condition here to get a and b. And then if you have a and b, you can substitute a and b into the general solution over here and get the particular solution. Similarly, for the Euler-Cauchy equation, the steps are the same, but the difference are the characteristic equation to convert to quadratic equation here and the y assumption here. But all the steps are the same. So after getting the general solution, substitute the values of initial condition given in the question, and finally you get a particular solution. Okay, so yeah, for if we plot this particular solution, you will eventually see that at the given initial that it satisfies the given initial condition here. For example, at y equal to 0, the value is at x equal to 0, the value is y here, the intersection here. At x equal to 0, the value is y, and the y prime at 0, y prime means the slope of the tangent of the curve is 7. So for the second one, for Euler Cauchy equation, when you plot this particular solution, you will see that this curve satisfies the initial condition here, whereby when the x is 1 here, the y value is also 1. And the slope here, y prime means the slope of the tangent. So the tangent here, the slope is equal to 1. Okay, this is just to make you understand what this initial condition means and why from the initial condition we can get only one line from the general solution which consists of multiple lines in a graph, or also called as a family of solution. Now let's answer quiz part C. If you haven't done the quiz, please answer first and then continue to watch this video. Okay, let's see how to answer the first question. So consider a chemical reactor system described by the following ODE. So 2C double prime plus 5C prime plus 3C equal to 0. If the initial concentration of the reactant in the reactor is 1 mole per liter and the initial rate of change of concentration is 7 mole per liter per minute, determine the specific solution of the ODE. So from the question we get that this is the ODE. So seeing from the C double prime means that this is second order, and in front of C double prime is a constant 2. There's no x term, so it's a constant coefficient, linear, homogeneous ODE. The initial condition given is at initial concentration of the reactant is 1 mole. So initial means x equal to 0 and the concentration is 1 mole, and the rate of change of concentration is 7 here. C prime is equal to 7. So knowing that this is a second order ODE with constant coefficient, this is the characteristic equation to convert to quadratic equation, solve the lambda, and from these two values we know that this is a distinct root, and since we know it's distinct root, we know the y assumption, and we can substitute into the general solution. Knowing lambda 1 and lambda 2, substitute into the general solution equation here, and you get the general solution. So since we are given the initial condition, substitute into the general solution and the derived general solution. So we will get A and B values, substitute it back to the general solution to get the particular solution. So this is the steps. Let's see the question for Euler-Cauchy equation. Consider a chemical reaction in a cylindrical reactor where the reaction of a reactant at a radial position and time is governed by the following differential equation. So R square d square C over dr square minus 4R dC over dr plus 6C to 0. If the concentration of reactant at R equal to 1 is 1 mole per liter, and the rate of change of concentration with respect to R at R equal to 1 is 4, determine the specific solution of the ODE. Okay, first thing first, it's better to simplify the given ODE to this term C double prime. So it's not really confusing. So the final ODE here is R square C double prime minus 4R C prime plus 6C equal to 0. Knowing that C double prime here is a second order derivative. So this is a second order ODE. And since there is an R squared term here and R here, this is an Euler-Cauchy equation, meaning that we will have a specific characteristic equation here with B minus A at the as the coefficient in front of lambda. And we also have a different Y assumption, which is R lambda 1 and R lambda 2. So after getting the lambda 1 and lambda 2, as usual, substitute into the general equation to get the general solution. Given the initial condition here, substitute into the C prime and C general solution and C prime, you will get the A and B. Substitute back into the general solution, you will get the final answer of particular solution. Now let's see for the second case for equal root, where we'll only have one lambda. Right, same step, we have same general solution. And so for previous case, for a distinct roots, we have y1 and y2, right? Because we have lambda 1 and lambda 2. Now, when we have equal roots, we only have one value of lambda. Remember? It's because the curve intersects at only one point at the x-axis. So we must have another assumption for y squared. So the second assumption here is x exponent lambda x. So substitute y1 and y2 into the general solution. We will have a different general solution for equal roots. And the difference here is the x in front after the term b here. And I also provide the derived general solution here in case it's needed later. So for Euler-Cauchy equation, same thing, we only have y1 because we only have one value of lambda. So we have to have another assumption for y2. And for this case, the difference here is there is an additional ln x in front of the x lambda. So substitute y1 and y2, the new y2 into the general solution. We have this general solution specific for cases only with equal root. And this is the derived general solution if it's needed. Now, let's see an example. So double prime plus 6y plus 9y equal to 0, given the initial condition. So still the characteristic equation the same, but the difference here is the y2 term here. So you will have a different general solution with the additional term of x here after b. So after you get the lambda, just substitute into the general solution. Given the initial condition here, substitute the value of x and y, you will get a and b. Substitute back to the general solution, you will get the final answer of particular solution. Second example for Euler-Cauchy equation. So different characteristic equation used here where this is b minus a. So after getting the lambda equal to -1, we know that this equal roots. Equal roots means we have different assumption for y2, whereby there is additional ln x over here. So substitute the value of lambda into the general equation, you will get the general solution here. Given the initial values condition here, substitute the value of x and y, you will get a and b. And again, substitute to the general solution here, you will get the final answer of particular solution. Okay, C, for complex root, where we will have, okay, similar the distinct, real and distinct roots where we have lambda 1 and lambda 2. So remember, for quadratic equation, when we have complex roots, the lambda 1 and lambda 2 has two terms here, a real number and imaginary number. So from these values, we have new terms for the complex case. So we have V and W. V and W can be obtained from lambda 1 and lambda 2. V is the real number and W is the imaginary number in front of the I value, the I term. All right, same like the two previous cases, same general solution. We have the same Y assumption for um, uh, for the Y assumption for case C is the same as case A because we still have lambda 1 and lambda 2. All right. So we substitute into the general solution here, substitute y1 and y2, we get the same general solution for the first case, case A, but since lambda 1 is imaginary, there are two terms here, real and imaginary. Also for lambda 2, then we have to substitute this term into the general solution. So after we substitute lambda 1 into the general solution here, lambda 2 into here, then after rearranging, we get a new general solution specific for ODE with constant coefficient for complex root. So the new constant are used here, which are C and D instead of A and B. So the step of getting this general solution from these two equations is shown in the next slide. I also provide a derived general solution here in case it's needed. Similarly, for Euler-Cauchy equation, we have different y1 and y2 substitute into general solution, and we substitute the V and W term into the general solution. After rearranging and everything, we get a new general solution for Euler-Cauchy equation with complex root. For similarly, like this general solution, the term now the constant used are C and D instead of A and B. I also provide the derived general solution in case it's needed. So if you are wondering why I provide this derived general solution is because in previous cases where the general solution is simple, it's not a big deal if you do manual derivation. But when we have this general solution and you want to derive it manually, then it will take a lot of time and there are high potential of mistakes or errors that you will do during derivation. So that will risk the final answer. So it's better if you can memorize or understand how to get the derived general solution. So you can save your time during your exam later. So if you are wondering how to get the new general solution with C and D, you can go through this slide, but I'm not going to go through this because it's quite complex and you don't need to know it. It's not that you don't need to know, but it's not really an important thing you can go through by yourself. All right, let's see an example for case C. Solve y double prime minus 4y prime plus 13y equal to 0. Using the same characteristic equation, you get lambda 1 in terms of imaginary number 2 plus 3i and 2 minus 3i. So you know that this is complex root. knowing that it's a complex root, you have to know what is V. V is the real number here, which is 2, and W is the imaginary number, which is 3. Now, let's substitute the V and W into the general equation that I provided in the previous slide. The substituting V and W, you will get a general solution here. Right. Given the initial condition, again, you can substitute the value of x and y and find the d value and c value. Substitute the d and c into the general solution. Then you will get the final answer of particular solution. Next, for Euler-Cauchy equation, solve x squared y double prime plus 3xy prime plus 2y equal to 0. Given initial condition, at x equal to 1, the y is 1, and x equal to 1, the y prime is 1. So this is the characteristic equation. Find the lambda, you will know that it is a complex root, and determine the v and w. Substitute into the general solution, general equation, and then you will get this general solution. But using the initial condition, substitute it to the y and y prime, you will get c and d. After getting c and d, substitute into general solution, and you will get the final answer of particular solution. All right. Okay, let's see the summary for second ODE with constant coefficient. I'm sorry, this is supposed to be EC, which stands for Euler-Cauchy equation for case A, B, and C. Okay, so the general solution for both cases. Okay, first, please make sure you understand what is ODE with constant coefficient and what is Cauchy-Euler equation. Remember to look at the coefficient in front of y double prime and coefficient in front of y prime. So for Euler-Cauchy equation, there will be x squared here and x in front of y prime. So the general solution for both cases are the same because this is based on superposition principle that applies for linear and homogeneous second ODE. So both are linear and homogeneous, so it applies to both types of ODE. But the assumption here are different because of the different coefficient in the ODE. So for this case, the assumption is E lambda x, and for Euler-Cauchy equation, the assumption is y equal to x power of lambda. Since the y assumption are different, the characteristic equation will be different. So here is the normal characteristic equation, but this one, the term here is b minus a. For case A, here, where the roots are distinct, where we have lambda 1 and lambda 2, the y1 and y2 are straightforward, where the lambda, here we just change to lambda 1 and lambda 2. After that, we substitute to the general solution, we will get a general equation for case A. For Euler-Cauchy equation, the difference is the y assumption, so we'll have a slightly different general solution for this case. Just for you to take note, this is the the derived general solution. For case B, for equal root, now you only have y1 because there's only one lambda, so we need a different assumption for y2. For this case, we have a x in front of exponent, and we have ln x for the case of Euler-Cauchy equation. So the general solution will be slightly different in terms of the second term over here and second term over here. Okay, C. We have the same y1 and y2 as distinct roots because we have 2 lambda, but we have a different general solution since if you remember previously, I've said that for complex values, we have a real and imaginary number. So this general solution is expressed in terms of V and W. So we also have a new term here, C and D. For we have so the difference here is the terms here, which comes from the y assumption. All right. That is all. So let's answer quiz part D. And if you have done the quiz, please scan here to submit your feedback. Okay, so that is all. Thank you very much. Have a nice day. And I hope you understand. If you have any question, don't hesitate to ask. Thank you. Bye bye.